Hi, good morning. I hope you all had a good coffee. They have very good coffee here. Thank you for being here today. We're going to talk about HTTP, or in fact, I'm trying to make you not use HTTP when it comes to microservices. I try to teach people to not repeat the same mistakes I did when I first started with microservices. So this thing doesn't seem to work. So my name is Irina. I'm a software architect at Endava in Romania, in Iași. I organize a .NET user group and I teach .NET on Saturdays. So today we're going to talk about monoliths and microservices, HTTP calls, different types, RPC, gRPC, and about messaging, and different types of messages that we're going to use in a project. So, microservices came up in this world after monoliths. I mean, there are the newer versions of monoliths trying to solve issues that distributed system has. So when we're coding and working on monoliths, well, we have an easy life as a developer. I mean, who loves monoliths? Yeah, come on, admit it. I personally love monoliths just because the life of a developer working on such kind of project is easy. I mean, yeah, you have more time because pretty much you press the build and you can grab a coffee and relax until the build finishes, right? And the deal with them is that are self-contained, single code base in a single technology, and a single deployable unit. Life is easy. Yeah, I kind of miss that life when I was working on monoliths because I knew one thing, dependencies were there. I mean, if you ever needed a class or a functionality, you simply, instantiate it or use it through dependency injection, and everything was there in your code. The fact with the monoliths is that all or nothing deploys. I mean, either it works, either it doesn't work. And the downtimes are pretty big in certain cases. And we have pretty much zero or almost zero continuous delivery. Why? Due to the large code base. It's hard to test. We always had a big team of testers that were doing every kind of possible test on each deploy, regression, smoke, and so on. And pretty much this is about the monolith. Another thing is about scaling. In certain cases, as a developer, we don't care very much about scaling the monolith, but we usually give bigger machines when we need to scale that monolith. We add more RAM, we add more CPU, and we can only scale up. I mean, this scaling up costs a lot of money, and doesn't guarantee that when you have a bigger machine, let's say double machine in power, you'll have double the power and double the requests served from your application. It's not guaranteed. And also, the money that you are spending or your client are spending on these monoliths, when they scale it, is not double in size. The only thing that is low as a budget is the storage. And to scale, we don't need always the storage. So we move on, we get more matured, and we start to split our monolith into pieces. We call them boundaries. And those boundaries should be single deployable unit managed by one team. But it should also have its own database that it only tries to add more overwhelming in our life. It's easy to deploy, much smaller code base, and it's standalone, easy to maintain. You have only one piece of vertical functionality that you need to maintain. But is it that easy with the microservices? We split the big chunk into smaller chunks, and in theory, everything should be more easy. But it also introduces complexity. We need a team of dedicated DevOps, and we have cascading effects on failure. If one microservice doesn't work, it might as well make other services or microservices fail. And you need to monitor them closely, more closely than with the monoliths. So, once you start doing this, you start to realize that these microservices are not so independent, because you all also need data from one another. And you start to have something like this. You realize you didn't do anything wrong, but you just need data from one side to another. And you turn out to something like this, or something like this. It's not wrong. It's the business you're trying to solve. But for example, do you know that Amazon calls 150 APIs to build a single page? No? And I have more. Netflix services 5 billion service calls per day. And from these, 97.7 are internal. We don't even see those requests. So we're thinking, if they can do it, we can do it, right? I mean, these are giants, we always look up to the giants, and we start doing microservices. And if you are inexperienced, you're going to HTTP calls. I mean, it's the go-to option. It's the first time you're trying to build microservices, HTTP calls. You're building HTTP clients, and everything just works, right? I mean, I did it, and it worked until a certain point. So what's the deal with HTTP calls? You issue a request, that request is processed, the response comes back, and you're happy. But what happens if the request doesn't come back? You're not so happy. And even more, you don't even know that request has been made. I mean, on the right-hand side, you don't know that you received the request. You have no clue about that request even existing. So I'm not going to talk about HTTP sync calls, right? We all know about them. But we need to think about all these non-functional requirements when building our application. It should be our main responsibility, except besides delivering the functionality our client needs or our application needs, we should think about availability in terms of microservices. Throughput, how many requests we're able to serve with success. Reliability. Our application is reliable to solve the business. Timeouts, how do you do about them? Latency. I mean, we're not always that lucky to have an Azure cloud or whatever cloud to host our application. How about retries or resilience? We never think about these things because as a developer, our main job is to deliver functionality, right? Pretty much. It's someone else's job to think of all these things. And also, these are the main important ones, but there are many others. So, there are voices in the industry saying that it's perfectly fine to use synchronous HTTP calls, but how about timeouts? API to API calls, how do you deal with timeouts? How do you do about availability? How do you ensure that every service you have is available? Are you going back to coupling? I mean, think of that. Creating an HTTP client, no matter how, in .NET, creates code coupling. I know, we often pack those HTTP clients into separate libraries, deployed with NuGet packages, and we say that we're safe. It's a separate deployable unit. I mean, it's a package, it's a library, I can use it everywhere. But you will just end up having dependency in your code, and that is not a good thing in terms of maintenance. And also, you can lose requests. And by losing requests, I'm saying that you don't even know you had a request. And we'll see in this talk about what I'm talking. Retries. How do you deal about retries? How do you do about retries? Thanks God, Poly library exists, and .NET Core 3.0 comes with retries out of the box if you know how to plug them, but you need to do them manually, and that takes out of your development time. Okay, HTTP calls, synchronous, everything, but how about async calls? Other voices in industry say it's perfectly fine to use them, that you are able to distribute load and serve more requests. But is it? The problems from HTTP synchronous are still there. It's just apparent that you are able to serve more requests. The load is the same. You can serve requests faster in appearance, but nope. So what we'll have in here, it's a simple API with a simple console app that pushes an I, that it's in a loop and it's increasing in size. So we're pushing these requests, and we're seeing 2,000 and something, 3,000 and something, in a time span of 20 seconds. And at the end, we saw that we pushed 3,501 requests in 20 seconds. Cool, that's a lot. But the deal is that the API our console app is calling is not started. I mean, these requests are pretty much done in vain. Into the network, the response doesn't come back, and the server, or the second API we are calling, doesn't even know we had these requests. So, talking in general about HTTP, it's synchronous by nature. No matter how we try to fake it, it's synchronous. This is the way they intended it to be. And another thing is that for each HTTP request we're doing, a new TCP connection is it's opened. That might add a few milliseconds at the total time of your requests. You have no retries out of the box with HTTP. You need to implement it manually. And you have no delivery guarantees. You cannot guarantee that the request reaches the end. Location transparency. Well, you need to hard code, you need to implement an AP gateway or something to be able to know where to call. But a good thing is that it works just fine for public-facing APIs. If it's public, you should go for this. And it's familiar, and everybody knows how to do them, and it's easy to debug. Yeah, you don't worry about correlations or anything else. And for client-to-client communication or API-to-API communication, it's not that good. Another challenges that you have in here is everything we talked in those non-functional requirements. Tracing, how do you trace requests? How do you route them? How do you deal with timeouts and the retry policies? In the retry stuff, you need to implement pretty much circuit breakers, everything that some books are talking about. And it's pretty hard, at least when you start dealing with microservices. Cool, enough with HTTP. How about gRPC? Now that is a first-class citizen in .NET 3.0. Whoever worked with gRPC? Okay, cool. Few of you. But gRPC is contract-based. Contract-based means that you have no code references, no NuGet package to depend on, no HTTP client made by yourself. And it uses HTTP 2, which makes it significantly faster. And it has efficient protobuf serialization. In terms that REST API and gRPC-based API will have will be more performant because it has smaller payload. This protobuf serialization is awesome, and the payload is super small. And it's available in many languages, and you also can have code generation. Okay, let's see a little bit gRPC. First of all, it's a file with proto extension in which you are defining your service. This is the contract that it will be used both by your calling API and your receiving API. So I'm defining my service as Fibo, and it has an RPC named compute Fibonacci, and it has a parameter and return a Fibonacci result. So I'm basically describing my service. And in the next part, we're describing the parameters. It's a type of requested number that contains a property of int32. And the second one is the result that has a property result. Okay, let's see a small demo about how gRPC works. So I'm going to show you a little bit of code. It is already available in Visual Studio. It's gRPC service as a template. You can also, let me show you the proto. So this is exactly the code I showed you. And I have a service that basically implements what is described in the contract. It receives a request of that type, and it simply calls something that computes Fibonacci. Easy as that. And the client that calls this, it's a simple console app. And as you can see, it's pretty much similar with the HTTP clients. You create a client of that type, and you pass it a channel. And what I did in here is to mimic a time span of 20 seconds in which I'm calling that client. And it pretty much works like this. So I'm going to open my Fibonacci server. That is going to wait for me to make calls. And I have this client that is a console app, and simply pushes requests to that. So from 0 to 41 gets back a response in a 20 seconds time span. The nice thing about it is that I have absolutely no code references. I mean, looking at the client, I only have Google Protobuf, gRPC core and gRPC tools, and no reference to my server. The only thing we have in common is the proto file that is the same. And this will, in production yet, I didn't see anyone using it, but it's much better than creating your HTTP clients and coupling code. Okay, so there are two separate entities that happen to share one file, the one that describes the service that you're using. Using modern CI/CD tools, you can deploy artifacts, you can make tests on them, and everything is much clearer and separated. So gRPC would be the next step from HTTP calls. And it's much faster, but still, you still have the same problem as you would have in HTTP. You need to monitor the requests, you need to retry, and so on. But you get rid of code coupling, and it's a big thing. Okay, gRPC out of the box, but there is another form of remote procedural call through a message broker. And how is this implemented? Who knows about RPC? The elderly ones. Yeah. Okay, so to put it simple, it's a kind of API call that is made through a message broker, in this case, ties system together, but preserve their own encapsulation, no code sharing, and makes external systems calls look local. The call that you're making in your calling application will look like it's in the same namespace, same solution, and so on. So how does this work? So you have a service, and you have a handler, and a request is made through. The handler will pick up that request, process that request, and send back that request through the same queue, which is very cool. Let me show you. So we'll have it in here. I think it's better to show you off screen than this way. Okay, so I have a server. I'm going to show you the code also. This server awaits requests. So I have a client that will push on the same pattern, 20 seconds time span, the requests with an I. And we wait 20 seconds to see what's going on. Still working. 20 seconds hasn't passed yet. We're waiting. Okay, they say that this numbers of requests has been pushed through compared to 3,500 in simple HTTP calls. So it's a big increase in throughput, right? So having a look in here, the server received our requests. Okay, how is it done? Well, I'm using RabbitMQ and we're going to talk about it. The intermediary between my service and my handler is this queue in RabbitMQ message broker. And through there, I'm going to do requests. But let me show another thing. I'm going to stop the server. OK. I'm going to clear the screen. And I'm going to run the application. So when the application starts, I'm going to do basically a request with 0 as a parameter. I'm going to stop the requests, and I'm going to do another one. OK, so I have like two requests now. OK, in HTTP, what would have happened with these requests if the server were down? Never reached the destination, never happened, correct? But let me show what happens if suddenly the server becomes available. See, we have the 2 requests, which increases the reliability big time. I mean, the requests that we were been making before are here. Yeah, they have the same parameter, but we didn't lose them. So it's a major thing. OK. Gain versus loss when using RPC through queues. You don't lose requests, and it's a very good thing. There are sensitive businesses that need availability and reliability more than anything else. If you want to consume faster, you can add more handler instances. You can spin up more handlers, and you will process the requests faster. You can apparently spread the load. For sure, you can process more requests. We compared 3,000 and something with 8,000 and something. But the deal is that is still synchronous. You're pushing a request through a queue, and at the other end, you're waiting for that response, and you need to match the request with the response based on a correlation ID of a kind. So you're still waiting for the other side to answer. But either way, it's a step forward from HTTP. OK, how about messaging? It's very modern nowadays. There are systems that really can handle messaging. So what is the message? I added in here an envelope with a header and the body, because pretty much this is it. You have a body that contains your data that needs to be transported. And the header has properties, custom properties that you can add, and standard ones. And no matter which tool do you use, you pretty much have the same properties to add in there. For example, correlation ID, property, reply to queue, and a few others. But those are the main important ones. A message, because we need to talk about what is a message. It's a single independent unit that can be processed independently, more or less. It's like a request from HTTP, but it has our business data in there. And it's serialized either in JSON, either in binary formats. So messaging and using a messaging system will give you loosely coupled integration. You won't have code dependencies. And a very cool thing is that it doesn't require both systems to be up. I mean, your server can be down. Your clients can still make requests. Those requests will be picked up as soon as your server goes up. Messages can also be transformed in transit. We're calling them enrichers. You can create messaging pipelines that will add or remove properties from their bodies, exactly like in CI/CD pipelines. You're creating a pipeline that does something. Let's call it, you have development, you have QA, you have staging. In the same manner, you can create pipelines to enrich or whatever, do something with your messages to be able to process them independently. The thing is that these messaging systems trade consistencies for availability. Involves often a producer and a consumer, or multiple producers and multiple consumers. And I have in here also a demo, pumping through a message queue, messages, 20 seconds time span, and we already have more than double throughput than RPC. Still 20-second time span. And I think it's going to stop. Yep. 38,000 in the same scenario in a similar machine. And I think we really need to look at it. Okay, async message processing, how does it work? Well, we have a sender or service, and we have a handler in this case. A request will be made through a queue. From there, will be picked up in a handler. But this time, the response won't go there. We'll go to other queue, where it will be picked up back by the service that initially sent the requests. In a similar manner, we can also create pipelines. You can put them one after another, and you simply increase throughput. You'll have availability in every NFR you can think of. Okay, this is the simple scenario when we need to simple process. But what happens if we add a database in the scenario? I mean, okay, pump in the queue as many messages as we can. As we see, almost 4,000 messages. But we need to store them somewhere. And it's usually the case. What happens with the database? Well, it's a reaction to the problems of distributed system. We can process more requests faster, don't lose them. But we move the problem to another system. Because the database and the connection will have eventual consistency problem, but this is a total different topic that needs a separate talk. Database connection is scarce. Depending on the system you are using, you'll have pretty much, 100 connections and so on. And at least you aren't able to have 40,000 connections opened to a database. I mean, that's a lot. And you need to solve the problem in a way. How do you do that? You can batch process the messages, you can use semaphores, but pretty much what you're doing is introducing more problems. So, okay, life is not that easy, but still, why use a messaging system with microservices architecture? Because of agility. I mean, it's faster development because you'll have teams that are independent, and these teams won't have an integration process. You depend only on a response, not on a code base that someone is developing. I mean, you have the contract, the message that is passed to the message body, and pretty much that's the contract. You do not depend on a team. You do not wait on a team to finish something to pick up from Nugget packages. You depend only on a response on a system. You do not care what is the technology in which that system is developed. You can have pretty much every technology you want in your different microservices. You can have a microservice in Go, one in Ruby, one in Python, and pretty much others in .NET or in Java. Why not? As long as the contracts are the same and they are made in a language that is common, like JSON and binary, you can decode them. Teams have full ownership and understanding of their code base. I mean, I remember the times when I had juniors in my teams working on a monolith. A lot of learning curve for them, or even for me when I switched projects. Okay, how about scalability? Yeah, we decided that it costs a lot of money to scale on a monolith, but in our case, we can scale up and we can scale out, but only the parts that are really needed. I mean, if the login is not used so often, or I don't know, there is absolutely no reason to scale that. If we have an intensive processing service that, I don't know, ingests a lot of data, it makes total sense to scale only that service, right? Because that will be a bottleneck for our system. So we can also give a bigger machine, multiple machines, and also only on those components in the system that are really needed. Yeah, don't scale the big block, scale only the parts that require this. Okay, increased throughput. Kinda HTTP versus messaging, big deal. Another thing that is very important for one system is elasticity. The same as cloud. You can scale up and you can scale down. You can spin up multiple consumers if the case. I don't know, there is a period in the business that will require lots of load. Makes total sense to spin up more consumers, to be able to process more. And a lot of utilities. Reliability, flexibility, distribution, increased throughput, scalability, elasticity, performance, agility, and fault tolerance. Because the system that we are using have everything out of the box. We do not care about implementing them. Okay, utilities, maybe there are only words on a PowerPoint presentation, but for a business, nowadays, these things matter, even more than functionality. Tools, frameworks, and systems. Amazon, Mass Transit, RabbitMQ, ActiveMQ, ZeroMQ, Kafka, and many others. We have plenty of options. The deal is, as soon as you worked with one of them, the same abstractions and concept apply to each and every one. So it's nice. The learning curve is big when you work with the first system, and then you can extend and apply it in everything. Okay, data types. These systems are split into 3 models. Queues, well, we all know queues from high school, actor model, and message brokers. Depending on in the situation, one or another might come in handy. So, queues. We have a sender, we have a receiver, and we pass those messages. And it's useful for point-to-point communication. We have a sender, we have a handler, pretty much this is it. It's point-to-point, one-to-one. Messages are ordered and time-stamped, and the consumer pulls the messages from there. One example is Amazon SQS, or Azure queues, table queues, but pretty much the principle is the same. First in, first out is timestamp and ordered. And this is the easiest messaging system, call it like this. Another thing is the actor model that is born from reactive programming. Actors are processes that can encapsulate behavior, can delegate and create new actors, can supervise the actor they created, and we have at most once delivery. An example for this is Orleans and aka.net. I really advise you to have a look on one of these. They're very popular nowadays. And they came to this model by inspiring themselves by the reactive manifesto that is saying that the application nowadays, modern ones, need to have loose coupling, async messages, location transparency, to be able to scale as fast as they can, to be able to self-recover and respond fast. The deal is that until a few years ago, a 3-second response time was acceptable. Nowadays, it's not. I mean, if you wait a page to load 3 seconds once, next time you won't visit that page. It's modern systems. So, let's talk about message brokers. Message brokers is like a control tower that handles everything that passes through it. For example, there is NATS that is used by HTC, Siemens, and VMware, ActiveMQ, and a lot of them, but big companies use them. One process in message broker, one process sends a message to a named queue or topic. You can have one or many consumers. It handles by default connections and disconnections. The server can go down, or a consumer can go down, and everything will be just fine when they go up. They have a concept that is called dead letter queue for messages that cannot be routed to different queues. You'll find them in here, but you won't lose them. They have 3 types of message guarantees. At most once, at least once, and exactly once. And depending on the business scenario, you can use one of those or each and every one of these. Different protocols, they are based on HTTP, or for example, Service Bus from Azure has 3 protocols, the default one from them, AMQP, and another one. But we're going to talk mostly about RabbitMQ because it's the easiest that I encountered. Okay, RabbitMQ. It's lightweight. Every queue is our first in, first out, and supports AMQP protocol. Easy to use, fast. It has at least once delivery. And the preferred protocol for it is AMQP. Advanced Messaging Queuing Protocol. If I recall well, it's a protocol invented by telecommunication companies a while ago. For example, JP Morgan used this protocol to process 1 billion messages a day. 1 billion, it's a lot. And it's also used in Ocean Observatory Initiative. It's an architecture that collects 8 terabytes of data per day using this protocol. And unlike HTTP, is async by nature. It has guaranteed message delivery in one of the 3 types, these 3 types. And a cool thing is that it has no DNS resolve. You have programmatic routing, retries out of the box, and you can acknowledge or not acknowledge messages out of the box. And also, it has the nicest channel concept that makes it very fast. It pretty much a channel looks like the wires in the picture. You'll open a TCP connection, and inside that TCP connection will be multiple channels that are able to transport data back and forth, but the same TCP connection. Unlike HTTP that opens a new TCP connection for each request. So this is one of the reasons that it's very fast. How can you route messages? For example, we can have point-to-point. We have routing keys that will help us deliver messages to handlers. For example, the color coding, red, blue, and yellow, depending on the routing key, will go to different queues out of the box. For example, image resize will go to the queue specified for it, the resizer that is a handler. So this is direct. Instead of RabbitMQ, you could have used, like, I don't know, Azure Queue. It's the same, it's point-to-point. But also, we can fan out. Once a message is received, the message is sent to different areas, different consumers. Also, so it's like a broadcast. I mean, okay, I received the message, send it everywhere, and let the consumer decide if it processes or not. But it will be sent to absolutely each handler. Topic, which is a very powerful and handy tool. You can define patterns on your messages, routing keys, and depending on the patterns, those messages will go to different consumers. Think about, let's say, different types of errors. You can log errors in Rabbit or any other message broker, and depending on the severity of the error, you can send them in different places, and then from there you can act accordingly. For example, if it's a critical error, then absolutely you need to intervene. If it's an information one, sent to a different queue and handler, you don't need to act on it. I mean, your business won't go down on that. So, this being said, I also have a few books for you. These are very cool, designing data-intensive applications and enterprise integration patterns. They're very useful in terms of distributed systems and handling big data, or large amounts of data, not necessarily big data. They have all kinds of patterns and all kinds of solutions and theory and information about these distributed applications. So, in summary, HTTP is not, apparently I lost a few slides. HTTP is not the only options. Distributed system is all about trade-off. I mean, you need to decide what's important for your business and for your system to be able to choose wisely. So, choose wisely. Choose wisely the messaging protocol that you're using. For example, I recently had a deal with Service Bus. The guys in my team were using the default protocol from Service Bus and SMB or something. And when switching to AMQP, we increased the throughput by 4 times. It's major. I mean, just a simple change of protocol could add multiple benefits to your system. So always try for AMQP when you're dealing with messaging. It's the fastest and the most reliable and most performant one. So thank you for being here today. And if there are any questions, I'm here.
Thank you for the talk. There is a question from me regarding a concept that already exists in gRPC. It is called streams.
Yeah.
When you can send not a single request, but a sequence of requests, for example, and then obtain a response from your service. Or there can be the opposite. So you can send a single request and then obtain a sequence of responses. Is there a similar concept in message-oriented middleware, and how can this type of communication be implemented?
Okay, thank you. for the question. So gRPC has like 4 communication models, and I totally recommend Steve Gordon's blog about gRPC. He has a lot of things on this topic. So pretty much the messaging systems, whatever they are, they treat each message as an individual bit, and it's your job to send it to consumers or handlers. The handler can also send back to the sender using RPC through queues, or it can send the message to other queues. But you cannot have like the streaming concept from a server to another API or from a client to another API. So there is not such a concept. It's pretty much unidirectional. Okay?
Hello, thank you for presentation. I have one question. It's about using messaging and, for example, direct calls.
Okay.
We had also a discussion yesterday. Someone said that you need to use only messaging, or someone say you need to use both in case you need, example, intermediate response, and you can't rely on queues which can be overflowed or something. So what's your opinion on this?
Okay, so regarding messaging and the usages of it, I totally recommend it for inter-service communication, because it simply cannot be used, for example, when we're using the browser, browsing the website. Okay, we can trigger a message downstream, but we cannot expect a response from the message broker in our UI. So it's a thing that I didn't mention in my talk, but it's pretty useful in downstream communication. Of course, a person might fake it, like the response from the queue in the user browser, but it doesn't work like this. And I would totally go for messaging, not always. It depends on the case. But bear in mind that whenever you are implementing something like microservices, you can go for HTTP, but always come back and evolve your architecture. Because by using microservices, microservices messaging, you can only make it better. I mean, the options and the benefits are huge compared to HTTP. But if you are at the beginning of your development, go for HTTP and then evolve. I did it, I admit. I made mistakes by using HTTP, but I also looked back and redid the things.
My question would be not about just messaging queue, but regarding you said that we need more handlers to deal with the data, and actually, how do you typically make the data consistent between handlers? I mean, single storage, or they both replicate to the same messages, or what should they do?
This is a very good question, because developing your application to treat these messages, they say like the messages should be idempotent. I mean, apply the same rule on your message. For example, think of, I don't know, event-driven architectures. You can replay events. I don't know how to put this. Let's take it offline. I lost my chain of thoughts.
Thank you very much for your presentation. And I'd like to ask one question regarding combining both AMPQ and HTTP protocols in one application for the case when we have some API which is accessible from the outside, so you have some clients relying on it. Are there any best practices or recommendations from your experience how do we await actually response when we are requesting some HTTP API, and then we rely on some services which are interconnected via AMPQ. So it's asynchronous by nature, as you said.
Yeah, in my experience, I also had this scenario. So public-facing API that calls downstream to get something. It's also useful, depending on the scenario, to use a cache between to prevent pipelines of messages going through when the public API is called. So, and you always refresh the cache from the handlers. That could be a scenario, a pretty valid one.
Thanks for the presentation. I just wanted to join to the previous question. I had a similar one, but I just wanted to quickly respond to that, if you don't mind. So if you're using something like end-service bus, they have such ability. So you send the message and then you're waiting for reply.
Yeah.
So you kind of combining asynchronous and synchronous worlds, right? But that's for the cases when you don't have a chance to rewrite your, for instance, REST API or something. You already have it. You can change your architecture. But my main question is basically whether you had a experience creating the system where everything is asynchronous. So basically, the communication with the clients is also goes asynchronously, like even through the REST, but you don't wait for response. You just send the command, and then you receive some reply back in some way. So what kind of ways, if you had such experience, what kind of technologies you used to give the reply back? There are, we can call some of them, but I just wanted to know your practical experience on that.
To be honest,
Thanks.
Unfortunately, no, I didn't have the chance to work on a such system, but I know my colleagues have used Kafka successfully for these scenarios. The actor model is more evolved, and it handles request responses back better than messaging pipelines. It's the only thing I know about it.
I was asking actually about some transfer protocol, whether you used like those push messages or like I don't know, long polling or singular or something like that to get
Signaler,
response.
of course, Signaler can be a valid option.
Yeah, but
correct.
If you use Signaler with the sockets, right? Those are pretty heavy if you go large scale. So
It is.
You have to find some other option there.
Distributed systems are all about trade-offs.
Okay, thanks.
Yeah, but bear in mind that not every system we will ever develop will support splitting the messages as in independent units or, I don't know, fully asynchronous and everything else. It depends exactly on the business scenario.
One more. You said that for public APIs we should typically use HTTP.
Yeah.
But as for single-page applications, maybe there would be.
I would recommend GraphQL.
There would be an option to. Would it be the option to connect them via middleware to some queue, because such things as React.js or something are really reactive and asynchronous from their nature? So maybe there is an option to connect them directly to the queue and receive the messages. And
of course, and you can react and send like your colleague said, the Signaler messages from the consumer.
But do you see any negative side effects from these decisions? I mean, for public APIs and such SPAs, maybe?
I mean, the public APIs should be like RESTful and easy to understand and scalable. If you put a queue in a way right behind the UI, I don't think it's possible, but if you try and do it with Signal or everything, your application might crash on a large scale of messages. For sure, that will happen.
The time for questions is end. Let's thank
I will
speaker.
be around here if. Thank you.